So yesterday's lecture looked at Timer2 interrupts. That's the way to call a subroutine every n clocks. Today I'd like to look at a couple examples of what you can do with Timer2 interrupts. Specifically, how to build a better wait routine so that instead of waiting approximately x clocks, I'll wait precisely x clocks, where x is the number of time in milliseconds. Build a stopwatch which is accurate to 1 millisecond. Generate musical notes from 440 Hz to 783 Hz, notes A5 through G5. Just those three. So starting out with a better wait routine. What we have before is a wait routine where I pass the number x, where x is the number of milliseconds I want to wait, then returns. What we were doing before is just kind of counting to a number in C, typically like 617. If I count that long, that's roughly 1 millisecond. It wasn't exact, but pretty close. With interrupts, I can make the timing precise. To do that, what I'm going to do is set up Timer2 interrupts so that every 1 millisecond, Timer2 is being called. The reason is 1 millisecond is a nice round number. I'll then, to do that, calculate how many clocks it needs to wait between interrupts, basically what n is. In this case, n is 10,000. 10,000 clocks means 1 millisecond. Find A, B, and C to equal 10,000. One solution is A is 10, B is 250, C is 4. And then I can initialize PR2 and T2 con. The interrupt initialization then looks like the following. PR2 is 249, T2 con is 4D, meaning A is 10, C is 4. Enable, enable. I'll then set up the interrupt service routine to have a variable called delay. Delay is a global variable. The interrupt is being called by hardware. I want to pass that data to the main routine. The only way to do that is through global variables. Again, as a subroutine, I'm not calling. The hardware is calling it. Everybody can see global variables, including the interrupt, including the main routine. Likewise, that's how we pass data to interrupts. What the interrupt service routine will do is look at the variable delay. If it's 0, do nothing. If it's not 0, decrement it. What happens is every millisecond, I decrement delay. So it's decrement to 0, stop at 0. Decrement once every millisecond. And also, I'm going to toggle port A pin 0. Only reason for doing that is so that I can see is the interrupt working. Now that I have the interrupts working, I will modify my wait routine to look like the following. When I call it, I'm going to set up the global variable delay, copy x over to it. So if x is equal to 1,000, delay is now 1,000. I then wait. As long as delay is non-zero, I'm going to sit here and wait in the while loop. After 1,000 interrupts or 1 second, I'll exit. That way, this wait routine takes precisely 1,000 interrupts. It takes precisely 1,000 milliseconds. Once I have that, I can now build a binary clock. You've got the interrupt service routine, the main routine where you set up Timer2 for 1 millisecond, and enable, 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 really enable, globally enable. And now I will, sorry about that. I will now have the main routine just delay once every millisecond and send the count to port C. I'll also send it to the LCD display. To illustrate this, I've got the following code. I'm going to call that subroutine wait, which waits 1,000 interrupts for 1 second. Increment time, sent to the LCD display. This isn't exactly correct. If you look at the output, the counting is a little bit slow. If I look at the frequency, the frequency on RE0 is correct. It is 500 Hertz. The timing is a little bit off because the routine takes 1 second to wait. The following code, incrementing time in the LCD move, takes about 14 milliseconds. So the total time is about 1,014 milliseconds. I can get around that. If I use the same idea in the main routine, what happens is I'm going to set delay to 1,000. That's my global variable. The interrupt service routine then is decrementing it every millisecond. The following code takes about 14 milliseconds to execute. The remaining 984 milliseconds is spent right here. As long as this takes less than 1,000 milliseconds, now the timing will be precise. and if you look at the resulting code, every 1 second precisely, the count's increasing. So there I've got a binary clock measuring time to 1 millisecond, even though the LCD routine takes about 14 milliseconds to be called. That's one application. Second application, let's build a stopwatch which is good to 1 millisecond. I've got timer 2 interrupts running in the background to 1 millisecond. I can now turn on and off a counter based upon the buttons being pushed. Let's set up a stopwatch so that when RB0 is pushed, I start the stopwatch. When RB1 is pushed, I stop the stopwatch. When RB2 is pushed, I clear the time. So what I'm going to do is have a global variable called time. That's how many milliseconds have gone by. And a global variable called run. Inside the interrupt surface routine, every millisecond this is called. I'll check the buttons. If I hit RB0, that means turn on the stopwatch. If I hit RB1, turn off the stopwatch. If I hit RB2, clear the time. And if the global variable run is equal to 1, meaning hit RB0, time is incremented every millisecond. In the main routine, I'll then turn on timer 2 interrupts for every 1 millisecond. That's the conditions is 1 millisecond plus turn on, really turn on. And then just display time. What that looks like is the following. I hit RB0, that starts the time. Hold on a sec. Sorry about that, I forgot to make port B input. I hit RB0, now the light turns on in port B. That turns on the stopwatch. RB1 turns it off. Stop. Start. Stop. Start. Stop. And RB2 clears. So now I have a stopwatch, good to 1 millisecond. That's a second use of timer 2, keeping track of time. Third application of timer 2 is generating a precise frequency. With this, you can build an 8-key piano. Now the number of clocks between interrupts is n. That's 10 million divided by 2 divided by hertz. The reason for the 2 is I have to set and clear 2 interrupts per cycle. With that, if I arbitrarily set A and C, I can calculate the number of clocks between interrupts for nodes A4 through A5, come up with A times B times C to roughly equal these numbers. And here it shows A is 12, C is 4. Calculate B. These are fractions. I can't implement a fraction with interrupts. It has to be an integer. With this, I can then set the number that B corresponds to for each note. Inside the interrupt service routine, I will simply toggle port A pin 1 every time the button is pushed. Any button on port B is pushed. Otherwise, the output is 0. You can change the conditions for an interrupt. For example, come back. Come back. If I set A equal to 12, C equals to 4, and then change PR2 in the program, that will change the frequency that's being generated, change the timer 2 interrupts. To change it, I'll just then check. If RB0 is pushed, change PR2 to the number corresponding to note A4, RB1 through RB7. To see what that looks like, let's go to here. And as I push the buttons, you can see that was 439.8 hertz. The next note is 494 hertz, 523.7, 588.8, 659.6, 699.6, a little flat, 795.8, 883.1. So I can build an 8-key piano. Some things you can do with timer 2.